All right. So let's start. I'm going to do something a bit different to begin. It's not something I usually do. I'm going to give myself the liberty of just talking for a bit without writing down a bunch of crap. So what I think is that it's easy to get lost in the weeds. We've been deriving things for the hydrogen atom for a long time, and it's nice to step back and look at the big picture, see where we've been, what we've accomplished, and where we want to go in the next handful of classes. So what I've done is I've drawn here just the standard three-dimensional coordinate system. So it has an X, Y, Z axis, and then I have the spherical coordinates on there as well. So what we're imagining is a heavy proton sitting at the origin of our coordinate system, and then an electron is somewhere in the vicinity. Just to appeal to like a classical picture, I've drawn the electron as if it's like a point. Clearly, it's not. But if we take that picture, then in spherical coordinates, we have a radial coordinate that is a vector from the origin to our electron. And then we can decompose into X, Y, and Z coordinates if we wanted to. Theta measures the angle from the Z-axis to the location. The way I like to think of theta is it's kind of controlling orbits around the origin. If we have a fixed radius and we just vary theta, we have something that's orbiting around the origin. And then there's this phi variable. Phi is going to control rotations about the z-axis. We're thinking about the proton and the Coulomb potential that it provides, the potential energy between the proton and the electron. It's spherically symmetric, and that means all that matters is the distance between the proton and the electron. It doesn't matter if we were to change the direction, change theta and phi, everything looks exactly the same for a fixed distance from the origin. And so what did we do? We wrote down Schrodinger's equation. The time-independent equation is the one that I'm thinking of. And we wrote it down in spherical coordinates, reflecting the spherical symmetry of our Coulomb potential. And then we said, okay, that's a nasty partial differential equation. How are we going to make progress? Well, what we tried to do is we tried to do separation of variables. And that was successful. We could separate into a radial part, a theta part, and a phi part corresponding to these different coordinates. When we did separation of variables, what it provides or what it allows us to do is to take our partial differential equation involving all of the spatial coordinates and separate it into individual ordinary differential equations involving only one of the coordinates at a time. I'm going to talk about it in an order that we didn't derive it. I'm going to start by talking about the radial part of the ordinary differential equation for the radial coordinate. So what we did is we applied a bunch of tricks to try to solve this thing. But ultimately, what it boiled down to was trying a series solution in the differential equation, which gave us some recursion relation for the coefficients. And we found that if we tried to take that recursion relation and we just allowed it to go arbitrarily long, we ended up with a solution that diverges. And we said, that's no good, because what does the time-independent Schrodinger equation actually tell us? We're looking for solutions of the wave function. And the wave function is a probability amplitude. If we square it, it's a probability density, probability per unit volume. If we integrate over all space, we need that probability to be finite. We need it to integrate to 1. That's our normalization restriction. So what we did is through separation of variables, we got an ordinary differential equation, say for the radial coordinate, but we're also going to impose other conditions on our solutions. And the condition that we're going to impose is that the solution has to be normalizable. what that meant, like technically, when we were solving it, is we had to truncate the recursion relation. And when we did that, we had to pick some fixed maximum j. It was actually j plus 1, where we said once we reach a certain value of j plus 1, we want all our coefficients to vanish after that. And that's kind of restricts the space of variables that we can use. It's like forcing the wave function to decay away as we go out to infinity. It has to decay away so that when we integrate it over all space, we don't get all that extra area under the integral that's going to make it blow up. And so in some sense, our potential is confining our wave function to a certain region of space, and then it has to decay exponentially outwards from there. I like to think of that in terms of like the kind of a parallel thought in terms of the infinite square well. The infinite square well is easy to think about because it has these rigid boundary conditions. We cannot let our wave function go past these large infinite potentials so that you have to go zero at the boundaries of the infinite square well. And then we can have standing wave conditions inside of there. So we can have either 0 nodes or 1 node or 2 nodes between those. And what those nodes are telling us is telling us the wavelength or how quickly our wave function oscillates. Why is that interesting? Well, it's interesting because momentum is h bar k, which is h bar 2 pi over lambda. So as we shorten the allowed wavelengths, we increase the momentum. And for the infinite square well, the energy of the particle in the well is all kinetic energy, p squared over 2m, or h bar squared over 2m. And so when you go to shorter wavelengths, you're going up in energy. Similar things happening for our hydrogen atom, except the difference is we don't have rigid boundaries where the wave function has to vanish. We have these kind of squishy, blurry boundaries where we have to slowly decay to zero. But it's still confining the particle. It's still restricting the amount of space that our wave function can occupy. And we solved the radial part of the wave function. I plotted some of them here. So this is the radial part. This is, it depends on n and L. And you can see if I take this purple one, it's n equals 1, L equals 0. That purple one, if we look at it, it has no nodes. It never crosses 0. It just asymptotically approaches 0. That's the decay as r goes to infinity. This is plotted as scaled by the 4 radius. So the 4 radius is somewhere around here, something like the average distance of the electron from the proton. And if we go much farther than that, quickly the probability of finding the electron there starts to go away. Okay, that's fine. So what if we went to n equals 2, L equals 0? That's the green curve. Well, here we do have a crossing. So this is in some ways very similar to the infinite square well. For the infinite square well, the first mode has no nodes. The second one has 1 node. And so we've seen the same thing happen here. If we go to n equals 3, L equals 0, we have this red curve, 1, 2, 0 crossings. And so that structure where the nodes are is determining the energy of our system. As we get more and more nodes, the energy is going higher and higher and higher. Just while we're here, let's look at this. There's n equals 2, L equals 1. That's the kind of cyan, light blue color. And so that one has no nodes. What if I went n equals 3, L equals 1? That's kind of another purplish one. That one has 1 node. It turns out that the number of nodes, number of radial nodes is n minus L minus 1. Okay, So let's just keep that in the back of our mind. So that's the radial part. And so it's really imposing normalization on the wave function that is leading to the quantized value n here that quantizes our energy. Okay, so let's go back then. We also solved other parts of the wave function. We solved the theta part. And what did we didn't do that in as much detail as we did the radial one, but it turns out that we ended up quantizing something else. It was this value L. L had to be some integer. Uh, so when we do that, if you were to do that carefully, it's also normalization that leads to the boundary conditions that give the quantization. So the normalization requires that when theta goes to 0 or pi, those are at the two poles, that the theta part of the wave function has to remain finite. So that's the new boundary condition. It leads to quantization of L. We haven't done it yet. We haven't completed it yet, but we're going to show that that is related to angular momentum, specifically orbital angular momentum. And it's actually, in my opinion, quite satisfying that this variable theta is controlling how things orbit around the origin, which is like an electron orbiting our proton if we want to have like a classical kind of picture in mind. Okay, what about phi? We also solved the phi equation. That one was easy. The boundary condition was that going around by 2 pi has to leave the probability density, the square of the wave function, unchanged. And so that's a symmetry about rotations around the z-axis. And what we found is that that led to a quantization of this number m. Well, we haven't done it yet, but where we're headed is we're going to associate m with the z component of the angular momentum. And angular momentum is like r cross p, and the z component of the angular momentum is going to involve the momentum and position coordinates in the xy plane. And we're going to think about rotations around that. And if there's rotational symmetry, that boundary condition led to quantization of what it's going to turn out to be the z component of the angular momentum. So we went ahead and we solved for these spherical harmonics, and this is what they look like. So let me try to explain what some of this coloring means. This rotation is meaningless. They just made it rotate so that we could get a 360-degree view of what the structure looks like. The coloring represents different phases of the wave function. Let me talk about more of the classical picture of what spherical harmonics really tell us. Imagine you had a solid sphere, like a chunk of steel, and it's been machined to be a perfect sphere. If I was to take a hammer and bang that sphere, it would start to resonate, it would oscillate. And the spherical harmonics tell you the different modes that that sphere could resonate in. And so red would represent, say, an outward oscillation, and blue would represent an inward oscillation. So the blue and red regions oscillate out of phase. So when one is going out, the other one would be going in, like so. The white regions are places where there's nodes in the structure, where the sphere surface is remaining fixed while other regions oscillate. And you can see at the top is L equals 0, then we go L equals 1, L equals 2, 3, and 4, and you can see as L increases, the structure of these modes of oscillation gets more complex. It's like a standing wave pattern. It's no different than plucking a string on a guitar and having or the infinite square well, having this one-dimensional standing waves. This is just a standing wave pattern for a three-dimensional structure. And so if you look at it, when you get to higher L, the wavelength of this standing wave structure gets shorter. We're going to find that as you go higher in L, that's going to correspond to higher values of orbital angular momentum. Okay, so if we look at the top one, that's L equals 0, there's 0 nodes. If we look at the second row, that's L equals 1, there's one white band around the circumference. That's one node. If we look at L equals 2, you see that there's two white bands, and there's going to be two nodes. So we also get increased number of nodes as we increase L. So if we go back to this picture, the number of nodes in the spherical harmonics is L. So the number of nodes in the total wave function, which is given by RNL of R, YLM of theta phi, is n minus L minus 1 plus L, which is equal n minus 1. So the nodal structure is determined only by n. You can have a certain value of n and different values of L. They all have overall the same number of nodes. And it's that nodal structure that's going to tell us about the energy of our hydrogen atom, or specifically the energy of the electron in our hydrogen atom. So that's why the energy depends only on n and not n and L, or that's at least an intuitive picture of why that might be the case. Okay, so what else could we say? Here is the hydrogen wave function. So this includes everything. It's the radial and the angular parts. And so let's do our node counting picture here. So let's see, what color do I want to use? I want a bright color for this black picture. Okay, they're not showing all of them. The first one they show is 2, 0, 0. The second 0 is M. Okay, and so I'm really focused on N and L for the moment. And if I go out from the center here and go outwards, what I want to do is I want to count how many times I go through a node where I'm not going to find an electron. And it looks like I go through one black ring. And so that is one node, and that is n minus L minus 1. Or sorry, that's just n minus 1. And so there it is. So that's one node. And then if I go to this one, and I go in a radial direction, oh, whoops. How many black rings do I cross? 1, 2 black rings, and so that's the n minus 1. Here, if I go n, let's see, which one do I want? Let's do this one. So here, if I start at the center and I go in a radial direction, I'm not going to count the 0 in the center. I'm just going to count where I cross a node. And so I cross 1, that is 3. Minus L is 2, minus 1 is 1, and so that's the one node that you get. You can also see in the spherical harmonics, you can look at them in another way. So in this representation, the way I like to think of it is this is telling me in which directions am I likely to find my electron. And so what I like to think about is, let's suppose I sit right in the origin of these plots, and then I look out in some radial direction. If I see a big lobe, then that tells me I'm likely to find an electron in that direction. If I look in some direction that's off axis of a node, then I see nothing, then I'm unlikely, I will not find an electron in that direction. So that's how you interpret these kinds of pictures. And then we have red and blue lobes. And so those are just sign reversals of the phase. And so that's going to be important when we think about interference effects. If you have some hydrogen atom interacting with a field or another particle, or you have overlap of wave functions between two different particles, in that overlap region, the relative phase of your two wave functions are going to determine how these particles interfere, and that turns out to be very important. Okay, so that's sort of my sort of large overview picture of what we're trying to do and where we've been and where we're going. All right, so what I want to do is I want to get back to thinking about angular momentum. All right. So go away. So we started a little bit, but I'm just going to repeat this so that it's all fresh. So angular momentum. In fact, maybe what I'm going to call it orbital angular momentum. Okay, so classically, L is equal to R cross P. Now, it's a bit weird to think about calculating orbital angular momentum of an electron that's not a point particle with some mass, but some probability amplitude smeared over space centered on this proton. Nevertheless, that's what we're going to try to do. And the approach is to replace all of the classical ideas of momentum by the quantum operators that we're already familiar with. So I'm just writing out the components of the angular momentum, the orbital angular momentum in terms of position and momentum variables. And in quantum mechanics, what we're going to do is we're going to say Px is going to be minus IH bar d by dx. Py is equal to minus IH bar d by dy. And Pz is equal to minus IH bar d by dz. So before we get too far into this, let me tell you, I'm going to give away the punchline. Let me tell you what we're going to find. We're going to find that the eigenfunctions of angular momentum operators, or operators built on angular momentum, are the same spherical harmonics that we've already calculated for the hydrogen atom. And so that means that the Hamiltonian and the angular momentum, it's going to turn out to be the total angular momentum, total orbital angular momentum, are going to be eigenfunctions of this, those two operators, the Hamiltonian and it's going to be L squared, are going to have the same set of eigenfunctions. That means we can know both of those simultaneously, and they're also stationary states. So once we prepare our system in a particular state with some energy and some angular momentum, it will stay that way. Okay, there will be no time evolution away from that state. All right, so let's get back into the weeds, because that's where all the kind of, I don't know, the beauty of this, the way that you get to see the big overall picture is by kind of grinding through all of the details. You don't get one without the other. All right, so we're going to try to find the eigenvalues of the angular momentum operators. As we do this, we'll actually find something slightly surprising. really what we're trying to do is we're going to try to show that this quantized L is related to angular momentum, and we're going to do that. We already know from solving the hydrogen atom that L has to be integer. What we're going to find that is a little bit surprising is that the analysis we do for angular momentum is going to allow for non-integer eigenvalues. Specifically, it will allow for integer values, but also half integer values, like 1/2, 3/2, 5/2, and so on. That is going to be curious. It's not going to play a role for the orbital angular momentum that we're trying to work out now, but we're going to associate with the electron a second contribution of angular momentum, and it's the electron spin, right? So we'll watch for that when it comes out. All right. So what we'll start with is trying to find the commutator between these angular momentum Lx and Ly. This part we wrote down, so maybe I'll go a little more quickly through it. But we'll just put in our Cartesian representation of Lx and Ly, and we can break this up into 4 separate commutator relations. Okay, so y pz minus x pz minus z py z px plus z py x pz. All right, and we discussed last time that, look, this pz is going to be derivatives with respect to z, but I don't have any z's anywhere in here. So it's probably not too difficult to see that that one's going to vanish. Likewise, we have a z here, but I have a y derivative and an x derivative. So that one's going to vanish as well. And I think this is more or less where we got to last time. Okay, so let's see. How could we write this? Let's try y pz z px. Okay, that's the first one we have left over here. And let's just write some of this out. Okay, so what's it going to be? Y pz z px minus z px y p z. All right. Well, what do we have here? We have a common factor of y, and we have a common factor of pz. Now, I can move these around. This is an x derivative, so I can move it past the z. This is y, I can move it past the z. In fact, I can move it past the x derivative as well. Same thing here, I can factor out the y pz. All right, so we have y, sorry, I said y pz, I meant y px. Yeah.
Sorry, I missed why we could cancel those out to 0.
Oh yeah, so if I write this out, this is going to be a d by dz, this is going to be a d by dx. But if I write commutators, the z and, the x and y derivatives aren't going to do anything to the z coordinate. Yeah. All right, so here we have, what's left? pz, z minus z pz. Okay, and so this is y px. And this is just a commutator of pz and z. Okay. So this first one here is going to be reduced to, there's a bit of a lag here. This is going to be y px pz z. And if you do the same kind of analysis for this one, you could write the second one that we have surviving here as x xpy z Pz. Okay. So what we have then is that this Lx, Ly commutator relation that we're trying to work on is y px pz z plus x py z pz. All right. Now, we've done stuff like this before. We did this commutator for x, px. It's the exact same thing for z and y and whatever you have. If you remember, this came out to be I h bar. This is the same thing, it's just in reverse order, so it's a minus I h bar. And so what we get is I h bar. And then we have xpy minus ypx. So it's xpy minus ypx. But xpy, ypx, that's just the z component of the angular momentum. So this is equal to I h bar Lz. Okay, you could do the same sort of trick with the other components. So if we did Ly and Lz, we would get I h bar Lx. If we did Lz, Lx, we would get I h bar Ly. These are relatively easy to remember because you just have to preserve the order of x, y, z. X, Y, Z. X, Y, Z. X, Y, Z. Okay. All right. I'm gonna put these guys in a box. And this is going to be equation star. So these are the fundamental commutator relations for angular momentum. All right. Now, you might remember from chapter 3 that we did the generalized uncertainty principle. And what we said is whenever two operators do not commute, then there's an uncertainty relation between them. So that is, we cannot simultaneously know both the quantities, both the eigenvalues with infinite precision. So from the generalized uncertainty principle, which I'll write down again, it was sigma a squared, sigma b squared has to be greater than or equal to 1 over 2i. Expectation value was a bit of stuff to write, but there's the commutator squared. So I want to do this for our angular momentum. So for example, it must be the case that if I take the uncertainty of Lx and Ly, and I multiply them and square them, that has to be greater than or equal to, well, let's see. It's 1 over 2i times IH bar LZ is the commutator. So the I cancels, I get an H bar over 2, and then I have the expectation value of LZ. Okay, so it's H bar over 2, expectation value of LZ squared. Or sigma LX, sigma LY is equal to, sorry, not equal to, it's greater than or equal to h bar over 2 times the absolute value of the expectation value of Lz. I put the absolute value here just because uncertainties are always positive. So you could in principle get a negative expectation value for the z component of the angular momentum. All right, so what this really means is Lx and Ly are incompatible observables. Just like x and px. All right. So I want to contrast this with another case. So in contrast, what I want to do is I want to consider the magnitude or the square of the magnitude of the angular momentum. So Lx squared, Ly squared, and now Z squared all added together. Okay, so what's going to happen if I do that? So we're going to consider the commutator between L squared and Lx. Okay, so that's going to be Lx squared with Lx. It's going to be Ly squared with Lx. And Lz squared with Lx. All right. This x is going to commute with itself. This Lx is going to commute with itself. And so this one will vanish. There was a way to handle products in a commutator relation. It was one of the assignment problems you had in the most recent assignment, I believe. I can write Ly squared commuting with Lx as Ly times the commutator of Ly and Lx plus Ly, Lx, the commutator, commutator of Ly and Lx times Ly. I could do the same thing with this one, and that makes it obvious that this one's going to vanish because it would be Lx, the commutator of Lx with Lx, and that's clearly 0. All right, and then we have to do the same thing for the third term. So we'll have a Lz, commutator of Lz and Lx, plus the commutator of Lz and Lx times Lz. All right. That's not so bad because we've already worked a bunch of these things out. Ly and Lx, where is that? Well, Lx and Ly is plus IH bar Lz. That means Ly and Lx is minus IH bar Lz. All right, so this is going to be minus IH bar Lz. So is this Lz. All right. And let's see, Lx and Lz. Remember, we said as long as we keep the order the same, we had like x, y, z. This is going to be plus IH bar Ly. Plus IH bar Ly. And so is this one. But look at what we have here. Then I have IH bar Ly Lz with a negative sign, and then I have an IH bar Ly Lz with a positive sign. So all right, there we go. And over here, we're going to have Lz Ly, Lz Ly. This one has a minus sign, this one has a plus sign. And so we get another cancellation, and this is going to be 0. So therefore, what we can conclude is L squared commutator with LK, where K can be X, Y, or Z, is going to be equal to 0. For K equal X, Y, or Z. And so that means I can find simultaneous eigenfunctions for the operators L squared and for any one of Lx, Ly, or Lz. Now, once I make a choice that I'm going to say find common eigenfunctions for L squared and Lz is the choice we're going to make. It's the conventional choice. Then that means I can't know Lx and Ly because we've already determined that if I know Z, I can't get Lx, and if I know Z, I can't get Ly. Okay, so we can find simultaneous eigenvalues for L squared and any component of the angular momentum. However, once we find one component, which is going to be Lz by convention, we cannot find Lx and Ly because of star, which is those commutator relations. Z is a nice choice to make because in our spherical coordinate system, phi controls rotations around Z. So it's a natural variable to use. Okay. So okay, that's like a 3-second delay or something. I ought to be able to find an eigenvalue equation for the operator L squared, where F is my eigenfunction. So this is going to be my eigenvalue for the L squared operator. And this is going to be my eigenfunction. Okay, at the same time, I should be able to take that same eigenfunction and add Z operator and get an eigenvalue for the Z component of the angular momentum. And so we're going to try to deduce what L and mu are. The way we're going to do it is going to appeal to some techniques that we used for the harmonic oscillator. We're going to use the ladder operators. Harmonic oscillators are fantastic. If anybody ever tries to tell you something about harmonic oscillators, you should listen because they come up over and over and over and over again in all fields of physics. So let's get to it. So we're going to use this raising and lowering operator technique analogous to what we did for the harmonic oscillator. The reason harmonic oscillators are so widespread, why they come up so often, is because what we're usually doing is we're usually looking for the behavior of a system near its minimum of energy or from small excitations about that minimum. And you could draw whatever shape of potential you like near the minimum. It always looks quadratic. And quadratic potential is harmonic oscillator. Systems tend to settle into these local minimum because there's almost always some kind of dissipation that takes energy out. And so if you start with a certain amount of energy, dissipation is going to suck energy out until you settle into a minimum of your potential. And at the minimum of the potential, it looks like a parabola. Okay, good. So the way we're going to define our raising and lowering operators for angular momentum is as follows. Lx plus or minus I Ly. All right. And what we're going to be interested in are, whoops, not that. I want my Z component. We're going to be interested in this commutator relation. Just like we found for the harmonic oscillator, we had this A plus operator. What it did is it increased the energy of our system by an amount h bar omega. So every time we acted with our A plus, we increased the energy by the same amount. And then L minus decreased the energy by some fixed amount. And what we decided for the harmonic oscillator, once we lower the energy down to 0, we can't lower it anymore. And we had to have L minus on the lowest energy state resulting in 0. So that's what we're going to do here. But we're going to try to find by how much does L plus and L minus raise and lower the angular momentum. All right. So here we go. So it's going to be LZ. Yeah.
Why did we choose L plus or minus to equal what it does? Like, was that just like an arbitrary thing you put up?
Well, it's not arbitrary. Smarter people than me worked it out and
Okay,
were following their lead.
We
Yeah.
didn't work it out at all.
No. Yeah. Yeah, I'm not that bright. So we're just following what people did. Yeah. Okay, good. So, some of these things we've already deduced. This was, remember, we just have to think about the order of X, Y, Z. X, Y, Z. I, H bar, L, Y. That better be what it is, and it is I, H bar, L, Y. This one is in the wrong direction, right? It's going to be X, Y, Z. So this is going to have a minus sign. It's going to be minus I, H bar, L, X. That must be what it is, and it is. Good. Okay, so this is equal to plus or minus I, H bar. And then what do we have? We have Ly plus or minus Lx. Sorry, let's do this slowly. I think I skipped a step in my notes, which is confusing me. So it's IH bar Ly plus or minus, well, in fact, it'll be minus or plus, I guess, Lx. Okay, so what I want to do is factor out, oh, sorry, no, I missed an I, didn't I? So let's do this carefully, minus or plus ILX. Does that make sense? I think so.
I don't know. You need the minus plus.
IH bar LY, and then I plus or minus I, but I have a minus sign here.
Yeah.
Oh, and so, and then I have another I here.
But that I you have factored out right now, so you need to bring the bit in.
Right. I can't do math in my head. So it's I H bar Ly, and then it's going to be minus or plus I squared H bar Lx. So this is going to be I H bar Ly, and then let's see, minus or plus I Lx. I think that's right. Wow. Okay. So what I'm actually going to do is say that this is going to be H bar I'm going to bring the I in. So I'm going to bring the I in. I'm going to get an I squared, which is a minus sign. So it's going to be plus or minus Lx. And then I'm going to have I Ly. And then the last step is I'm going to factor out the plus or minus. And so this is going to be plus or minus I Ly. So if I have the plus sign, I get plus Lx, and I get plus I Ly. That works. If I have the minus sign, I get minus Lx, and I get still plus I Ly. So that's good. All right. Good. So finally, we got there. But if you look, Lx plus or minus I Ly is exactly the definition of L plus minus. So this is L plus minus. And so our result is that Lz, L plus minus, is equal to plus or minus h bar L plus minus. All right. So what are we going to do with this? What we're going to do is we're going to say because L squared commutes with both Lx and Ly, that means that L squared L plus minus is equal to 0. Okay, so therefore, L squared and Lz L plus minus commutes with L squared. So it can have a simultaneous eigenfunction with L squared. And so these can all be simultaneous eigenfunctions of f. So let's consider L squared, L plus minus f. Well, what's that going to be equal to? L squared and L plus minus commute, so I can switch their order. We can switch orders of L squared and L plus minus because they commute. Okay. But we previously said we're going to try to find the eigenvalue of L squared acting on its eigenfunction. We, for the moment, have labeled that eigenvalue as lambda. And so what we have is lambda times f, which is equal to lambda L plus minus times f. Okay. So if we compare this to this, L squared is also, or L plus minus f is also an eigenfunction of L squared, and it has eigenvalue lambda, the same eigenvalue as L squared has when it acts on f. All right, so L plus minus f is an eigenfunction of L squared with the same eigenvalue, which is lambda, as L squared acting on f. All right. I know this is all a little abstract, but we're going to bring it together soon enough. I want to do the same kind of game with Lz acting on L plus minus times f. All right. But we're going to have to be a little more tricky this time. So what I'm going to do is I'm going to say, I'm going to write this as LZ, L plus minus F. Sorry, I'm going to factor this out. Actually, I'm going to put F here. Okay, so far the left-hand side and the right-hand side are exactly the same. I've just written it in a kind of two different ways that are equivalent. So the trick is I'm going to subtract something off here. I'm going to subtract off L plus minus LZ. And I can do that as long as I add it back on over here. Okay, good. Why did I want to do that? Well, we can write this as the commutator of LZ and L plus minus. But we've already worked that out. There it is. It's plus minus H bar L plus minus. Okay, so it's plus minus H bar L plus minus. So we're starting to use some of these results that we've worked out. And we already said LZ is going to be an eigenfunction of F. And we, for the moment, have identified its eigenvalue as mu. We don't know what it is. We just said, let's call it mu for now. So this is mu times F. Okay. So what do we have here? We have plus minus H bar, L plus minus acting on F. Okay. So this is, let's see, we have a mu, and then we have plus minus H bar, sorry, H bar, and then both terms still have L plus minus on F, L plus minus on F. So we have L plus minus on F. Okay, good. So L plus minus F is an eigenfunction of LZ with eigenvalue mu plus minus H bar. And now you can start to see what we were aiming for. For the harmonic oscillator acting with A plus, increase the energy by H bar omega, A minus, decrease the energy by H bar omega. So now L plus acting on F is going to increase the Z component of the angular momentum by H bar, right? Mu was the eigenvalue of the Z component of the angular momentum, and acting with L plus increases it by H bar. Acting with L minus decreases it by H bar. So L plus increases the LZ eigenvalue by plus H bar. L minus decreases the LZ eigenvalue by, I guess I don't need plus H bar. It increases it by H bar or decreases by H bar. Now, we could never have the LZ eigenvalue mu greater than the magnitude of L, right? Think of it. LZ is a component of L. And so it would be impossible to have a component of L be bigger than the magnitude of the total vector. That's clear. Or mu cannot be greater, greater than the eigenvalue of L squared was lambda, so that the magnitude of L is the square root of lambda. Greater than square root of lambda. So likewise, we cannot have LZ be less than minus square root, sorry, I should say mu minus square root of lambda. So I could have a Z component that's positive and it can't be greater than L. I could have a Z component that's negative. It can't be more than minus L. And so these together restrict the range of mu. How we do? 15 minutes. All right. Oh, no, not looking good. Okay. So if we are in a state, let's say FT. FT is going to be like the top state of our angular momentum with maximum LZ eigenvalue. The reason they use top is because Griffiths has this picture of a ladder for the ladder operator, and this is the top of the ladder, the top rung. We can't go any higher. So it must be the case that LZ acting on the top eigenfunction gives us the maximum value of mu, and we get our top eigenfunction back again. And what I'm going to do is I'm going to define that as J H bar times F top. Let's think about angular momentum. Angular momentum has units of R times momentum. So it is meters times momentum is kilograms meters per second. So overall, it's kilograms meters squared per second. But that's a joules times seconds. And that's exactly the units of H bar. So H bar has the units of angular momentum. So I'm going to pull that out. And then J is some dimensionless quantity. So this J is unitless because H bar has units of angular momentum, which happens to be joule seconds. All right, fair enough. And then if we took L squared and act on F top, we just get whatever the eigenvalue is. We called it lambda times F top. And the other thing that we require is that we cannot raise the Z component of the angular momentum anymore. We're already at its maximum value, so this has to be 0. All right, good. So now L plus minus, L minus plus is the next thing we're going to consider. Oops, L plus minus was Lx plus minus ILy. And then L minus plus is going to be Lx minus plus ILy. And so let's just grind it out. Let's multiply this stuff out. Lx squared. I'm going to do this times this. the plus minus times minus plus gives me a minus. But then I have an I squared. That gives me a minus. So overall, we get a plus. And all that's left is Ly squared. And then we have our cross terms. And so our cross terms are going to be, I'm going to write it as minus plus I. And then what do we have? The minus plus I. So we could have a Lx times Ly. And then I'm going to do minus. I'm going to do Ly times Lx, but that's plus minus. So I'm going to put a minus sign in here so I can have my minus plus out front. This is Ly Lx. Well, we've already seen this a bunch of times. This is the commutator of Lx and y. Remember, it's just the order of the indices x, y, z. So this is going to be IH bar Lz. IH bar Lz. Okay. But we could write this in a nicer way. If this was Lx squared plus Ly squared plus Lz squared, we would just say that's L squared. So I'm going to do that. I'm going to say this is L squared minus Lz squared. Okay. So L plus minus L minus plus is equal to L squared minus Lz squared. And then let's see. Okay. I times I is minus 1. So our minus 1 is going to turn this back into a plus minus. So it's going to be plus minus H bar L Z. Or L squared. Remember when we did the raising and lowering operators for the harmonic oscillator? We ended up writing the Hamiltonian in terms of A plus and A minus, right? It was, I forget what it was, but it's something like H bar omega bracket A plus A minus. It was either plus or minus a half closed bracket. So we're doing the same thing. We're writing our angular momentum operator, the square of L, in terms of our raising and lowering operators, doing the exact same stuff. So we solve for L squared. So we have the L plus minus times L minus plus, and then we're going to have plus Lz squared. Now we're back to a minus plus H bar Lz. This thing's important enough that we'll give it a label. Okay, good. So what I want to do is I want to act with that new version of the L squared operator. And what I want to keep in mind is that if we act on the top state, the highest Lz eigenstate, if we act with L plus, we have to get 0. Okay, so what I want to do is I want to act with this thing on our F top. And I want to get 0. So I don't want the minus sign, because the minus sign acting on F top will just lower the angular momentum. That's allowed. I want to take the bottom signs, because then when L plus acts on my F top, that has to be 0. So therefore, taking the bottom sign of star, right? So we've kind of written L squared in 2 different ways. We can take the top signs or we can take the bottom signs. I'm going to choose to take the bottom signs now. And I'm going to take this new L squared. I'm going to act on our F top. What do we know? We know that L squared has an eigenvalue lambda. But now what we could do is we could also say, well, L squared is also, I'm going to take the bottom sign, L minus L plus Lz squared plus H bar Lz. F top. I think we're going to find a nice natural place to stop here, actually. I wasn't feeling great. I feel a little better now. Okay, so just to do this slowly, let's expand this out. Plus LZ F top plus H bar LZ F top. Okay, so things are going to get a bit nicer. We cannot raise above the top Z component angular momentum eigenstate. That has to be 0. LZ F top. We said that was mu maximum times F top, the maximum Z component of the angular momentum. But we said instead of writing mu maximum all the time, I'm going to write that as JH bar. So this is JH bar F top. Likewise, this is JH bar F top. Okay, and so what are we left with? Well, the zeros, that's nice. I like zeros. JH bar LZ acting on F top. Plus, let's see, H bar squared times J. Or JH bar squared F top. But this is just another JH bar F top. And so what we get is L squared F top. We said that's equal to lambda F top. And now it's going to be equal to, let's see, H bar squared, H bar squared. Okay, both terms have an H bar squared. All right. Both terms have the eigenfunction. That's good. And let's see, what else do we have? We have a J squared and a plus J. So, okay, so that's different. So we have J squared plus J. And usually the way people write this is lambda has to be equal to H bar squared. I can factor out a J. So it's H bar squared, J plus 1. I'm going to call this equation A. And this is a nice place to stop. Let me tell you what we're going to do next time. We're going to repeat this thing. In fact, you should really do this on your own and work it out yourself before we do it on Monday. What we're going to do is we're going to say, let's take L squared and act on the bottom state of our ladder, where there's a minimum of the Z component of the angular momentum. Okay, L squared on that eigenstate is still going to give us lambda. So we're going to have lambda equal some stuff. This time, we're going to rewrite L squared, but we're going to take the top sign. Why are we taking the top sign? Because we're going to have an F bottom here. And if I take the top sign, I'll get an L minus right there. And L minus acting on the lowest angular Z component angular momentum state cannot lower it anymore. So we have to get a 0. And then we'll just have to deal with only these things. And we're going to get a second expression. We're going to get equation B. Lambda is going to be equal to some stuff that involves H bar and J's. And we'll have 2 expressions for lambda, and we'll try to figure out how to bring them together. Okay, so we're almost done actually working out some of this eigenvalue stuff. We'll complete it on Monday. All right, thanks very much. Have a good few days.